Now, we are moving into the fourth example. This has the infinite number of states. Suppose the state space, let me draw the state transition diagram, state 0, 1, 2 and so on. The left hand side it has the states -1, -2 and so on. So, the state space of this Markov chain has a countably infinite number of elements with the state 0 plus or minus 1 plus or minus 2 and so on. Let me give the transition rates, transition probabilities. So, the system is moving from state 0 to 1 with the probability p, and the system is moving from the state 0 to -1 with the probability 1 minus p. Therefore, if you see the state transition diagram, state one step transition probability matrix, the row sum is going to be 1. So, you keep p lies between, p can lies between 0 to 1. Similarly, you go for the all other states. The system is moving from the state to the forward one state, that is with the probability p, backward state with the probability 1 minus p. With the forward is p and coming back to the one step less, one state less, that is 1 minus p. So, this is the way it goes for all the states. 1 minus p and this is 1 p, and you have a countably infinite number of states. Fine. Now, let me go for the case 1 in which the p is going to be 0. Suppose p takes the value 0, what happens, or how to classify the states when p is equal to 0 in this time homogeneous discrete time Markov chain. When p is equal to 0, there is no forward arc. When p is equal to 0 implies the system is always go to the one state, one step less, one state less with the probability 1, because p equal to 0. Therefore, you should be able to visualize what is the state transition diagram corresponding to p is equal to 0. There is no forward arc arrows. That means, whenever the system start from some state, it will keep on going to the one state less in every step, and you can visualize for a longer run where the system will be, whether it will be in the positive side or in the negative side. You can visualize whenever the system start from any finite state over the period, it may be in some state with some positive probability for the finite number of steps, for a infinite number of steps, or for a longer run the system will be in the negative side for a longer run. So, that is a limiting distribution, but here we are discussing the classification of the states. Therefore, with the probability 0, it will not be back at all. If the system start from any state, it will not be back to the same state with the probability 0. Therefore, all the states are going to be, the transient states. If you calculate f for, you take any finite state 1 or something, then f 1 1 of 1, f 1 1 of 2 and so on. If you calculate, then you may land up f 1 1 capital 1, that is going to be always less than 1. Therefore, if you start with one state, you can conclude it is a transient state, and all other states also are of the same way. Therefore, all the states are going to be same. Suppose we discuss the case 2 with the p equal to 1, what happens? If p equal to 1, then you have all the forward arcs, not the backward arcs. That means, whenever the system start from any state, then the system will go to the forward all the states in subsequent steps with the probability 1. In a longer run, the system will be in the positive side, positive infinite side in a longer run. Therefore, with the probability 0, it will be in any one of the finite states in a longer run, whereas for the any finite steps, the system will be in some of the states and it will be keep moving forward state over the number of steps. Therefore, here also you will end up all the states are going to be transient states. Both the two cases, the situation for the limiting distribution may change. One is in the left side, the other one is in the right side, whereas all the states are going to be the transient states. But our interest is for the P is lies between, that is our third case. Our interest is P lies between 0 to 1, open interval. That means if you see the previous state transition diagram, you have both the forward arcs as well as the backward arcs, because the probability P is lies between open interval 0 to 1. Therefore, the 1 minus P is also lies between 0 to 1 in the open interval. Therefore, whenever the system starts from any state, it will come back to the same state with the even number of steps. Suppose you visualize with the state 1, it can come back to the same state 1 not in the odd number of steps, but in the even number of steps. Suppose if the system moves to the state 0 in the first step, and in the second step it can come back to the state 1. Similarly, suppose the system would have moved from 1 to 2, then in the second step it would have come to the state 1. Therefore, it is a 2 steps it can come back, either via going to the state 0 or going to the state 2. Suppose you go for think of 4 steps it coming back to the same state, that is possible. Need not be the first visit, means it can make a 2 times loop in the left side, or it can make a 2 times a loop in the right hand side, or it can make a 1 step forward and 1 more step forward, then it can come back. Therefore, all the possible steps, if you include all the possible steps, you will come to the conclusion it will take a even number of steps to come back to the same state. So, if you do the simple exercise what we have done it in the earlier case, you can come to the conclusion 0 plus or minus 1 plus or minus 2 and so on, all the states are going to be a recurrent state. Without fixing the value P, you can conclude Fii, capital Fii is going to be 1 for all these states. Therefore, now we come to the conclusion all the states are going to be the recurrent state. If you try to find out the periodicity for any state, the way I discussed, the greatest common divisor of the greatest common divisor of n such that the Pii of n, which is going to be greater than 0, and this is possible for all the even number of steps. Therefore, the system will be come back to the same state 2 steps, 4 steps, 6 steps and so on. Therefore, the GCD is going to be 2 for this particular Markov chain. So, the period is going to be 2 and the recurrent state. Now, our interest is whether these states are going to be a positive recurrent or null recurrent. But for that you need what is the value of P, because without P, without the value of P, you cannot come to the conclusion the mu suffix I that is going to be n times Fii of n. You need the value, but some example it is not, it is possible, but still by supplying the value of P or what is the range in which you can conclude whether this is going to be a finite quantity or going to be infinite quantity based on the range of p, you can conclude these recurrent states are going to be a positive recurrent or null recurrent. Since the state space is going to be 0 plus or minus 1 plus or minus 2 and so on, and all the states are going to be a recurrent states, it will form a one closed communicating class. Both are all the states are communicating with each other. Therefore, you will end up having only one closed communicating class which is same as the state space. Therefore, this is going to be a irreducible Markov chain. These states may be a positive recurrent or null recurrent based on the range of p, but here we are just concluding this is going to be a irreducible Markov chain with all the states are going to be a recurrent with the period 2. So, since the period is 2, it won't be a ergodic states also. If you want a ergodic state, you need a positive recurrent as well as the aperiodic. Since the period is 2, you can conclude this is not going to be the ergodic state.